Boom! Human. So we're continuing with our series on logs. Alright, in the last video we will just discuss the very faint outlines of the beginning of the topic, where we define what a log is. We use the definition to derive a mathematical equation in the exponential form, and then we went further with the definition and we switched from the exponential form to the logarithmic form. In this video, what we're going to do is illustrate the concept by using an actual number. The number we're going to use is the number 64. 64 is a very convenient number to illustrate the concept of logs. Alright, so look at it. So if I tell you that the log of 64 is 1, alright, I say that the log of 64 is equal to 1, and then I come and I tell you that the log of 64 is also 2, and then I come and I say that the log of 64 is 3, and then I come and I say that the log of 64 is also 6, and then I come and I say that the log of 64 is 64. How can the log of 64 be 1, 2, 3, 4, 5 values? The log of 64 could be anything. Alright, so we choose some integer values that people could grasp quickly to illustrate the point. Alright, and then we have a couple other values to slip in as well, and then we'll just demonstrate that the log of 64 could be anything. How can the log of 64 be equal to anything? Because if you recall from the last video, this is the power, this is the quotient, but watch it, the base is missing from each of these equations. Good? So if it is that the log of 64 could be 1 or 2 or 3 or 6 or 64, then clearly the quantity that is changing here must be the base, right? Because the quotient is the same. We have the same 64 running right through, but we have a different power in each case. And if the power is different, then the base must also be different. Good? Now, if I say to you that the base here, and I'm going to change the color now. Let us use blue for the base, blue for base, right? So let us say the base is 64 here, and let us say that the base is 8 here, and let us say that the base is 4 here, and let us say that the base is 2 here, and let us say that the base is 1 here. Good? So log of 64 is 1 only if the base is 64. The log of 64 is 2, but for that to be the case, the base has to be 8. The log of 64 is 3, also 3, but that could only be possible if the base is 4. The log of 64 is 6. That is only the case if the base is 2. And the log of 64 is actually 64, but that only happens if the base is 1. Where we get that from? Where that come from? Right? I didn't just choose these numbers out of a hat. Right? This is serious matters here now. Good? This is the case because, I'm going to write this in red now, 64 to the power of 1 is equal to 64. So in other words, 1 is the power to which your base of 64 must be raised to give you back a quotient of 64. 64 to the power of 1 is equal to 64. Your base is 64, raised to the power of 1 is equal to 64. The log to the base 8 of 64 is 2. That is so only because 8 squared is also 64. So the base is 8, the power is 2, and the quotient is 64. The log of 64 to the base 4 is equal to 3. That is so only because 4 to the power of 3 is 64. So 4, which is the base, to the power of 3 is equal to 64. Base to the power equal quotient. The log of 64 to the base 2 is equal to 6. That is only so because 2 to the power of 6 is equal to 64. Again, the base is 2. Base is 2. 2 to the power of 6. 2 to the power of 6 is equal to the quotient 64. Equal to the quotient 64 here. And then, of course, the log of 64 to the base 1 is equal to 64 because 1 to the power of 64 is equal to our good friend 64. So with a quotient of 64 and a base of 1, then the power itself must be 64. So the log of 64 to the base 1 is equal to 64. Good? So this, I think, is a very good illustration of the whole idea of the log, which is represented by the power, and it shows the importance of the base. Now further on into the topic, there will be times where the base will be assumed. There will be times where the base will, you wouldn't really need to state the base, but those things occur under special conditions, which we will get to a little later. Okay, so just to complete this video on logs, alright, I could say, for example, that 64 is equal to 32 to the power of 6 over 5. We know that 6 over 5 as a fraction is the same as 1.2 as a decimal, so we could also say that 64 is equal to 32 to the power of 1.2. We could say also that 64 is equal to 16 to the power of 3 over 2, which is the same thing as 16 to the power of 1.5. 1.5, of course, being the decimal equivalent of 3 over 2. Good? So we introduce a little variation here now. Instead of whole number powers as we have worked with up to this point, 2, 3, 4, 6, whatever, we now introduce in fractions. Right? We have improper fractions in these two instances here. We could also have regular fractions, something to the power of 2 over 3, something to the power of 3 over 4, etc. We will deal with those fractional powers in a separate video at a later date. Good? But this is just to kind of round off the discussion of 64 as an easy number that we could use to illustrate the concept of logs. Alright? So, given that we have these two exponential equations, we could then write in logarithmic form that the log of 64, alright, let me start with this one here. The base is 32. Log of 64 to the base of 32 is equal to 6 over 5. Let us write it as 1.2. Right, just to start getting you acclimatized to the fact that once we start dealing with logs, more often than not, we will have decimals in the picture. Good? And we could also write that the log of the same 64, this time the base is 16, is equal to 1.5. Remember, of course, that the log is the power that you're raising the base to. Good? So that's basically it. Alright, we will continue this discussion of logs in a subsequent video. Alright, so just stay tuned, look out for it.